So I think this is where we left off, isn't it? Is that so? I think so, yeah. I think we talked about, the scientific notation, and we kind of figured that, when you can write the number in the scientific notation if you use the powers of 10, right? So for instance, like in this example, these two zeros are not significant figures. They're placeholders, so you don't really need them. So you can get rid of them writing, a significant figure 3, okay? And you kind of have an example here that only the first zero is significant, meaning that only this zero in the center is significant, okay? So write 3.0, you keep the same number of significant figures, 2 significant figures. So these 2 are significant. You keep this 2, but you write it in a slightly different way, okay? So, and as we mentioned before, if you want to write down a big number, you use 10 in the positive power. So convert here. There's only one significant figure, which is 4. Okay, so you write 4 multiplied by 10 in the power of 5. You basically replace 5 zeros by 10 in the power of 5. That's equivalent. Does that make sense? And here, you basically say, okay, we have 2 significant figures, we keep them, 8.5. But in order to demonstrate the actual number, we need to multiply 8.5 by 10 in the power of 5 to maintain this parameter, this number. So in the test, you can expect seeing sort of what is the scientific notation for such and such? What is the scientific notation for such and such? Am I clear? It's going to be pretty straightforward, a lot of numbers on the first test. Okay. And similar way, we used similar approach when we write scientific notation for numbers that are less than 1. But we use 10 in a negative power instead. So here you have one significant figure, 4, okay? So you keep it, but you write down, you count how many times. Here's maybe a better explanation. Let me erase this crap and provide you with maybe a better explanation. So you see where the decimal point is, okay? So move decimal point 5 points. You move it to the right in order to get 4. Let's count how many times. 1, 2, 3, 4 times, right? You move it to the right 4 times. We're clear. You follow me? So since you move it to the right, it's going to be 10 in the negative power. You moved it 4 times, 10 in the negative 4. Does that make sense? In this example with 850,000, decimal point is here. Can you see the tiny little decimal point? Okay, so you move it to the left. You move it 1, 2, 3, 4, 5 times. You move it to the left, it means that it's going to be 10 in the positive power, 10 in the power of 5. 8.5 multiplied by 10 in the power of 5. So basically what you need to remember for the scientific notation, if you move decimal point to the left, 10 is going to be in the positive power. If you move decimal point to the right, it's going to be in the negative power. Got it? Moving on. Now, let's figure out the difference between the measured and the exact numbers. So, measured number is when you measure length or mass using scales or volume using cylinder, measured. We're clear. Exact numbers, they aren't measured. Let me explain. 6, 12, 18, 23, 24. That's exact number. Countable pieces. Does that make sense? So there are 24 people in this room. You can't count with a certain degree of precision. You can't say there are approximately 24 people in this room. That's countable number, 24, all right? We counted each and every person. So there are no, significant figures cannot be applied to the exact number because, well, it's exact. Does that make sense? So, like, fingers on your palms. 10, right? Is that exact number? Yes. You measure the length of your fingers, all of them, and put it all together, all the measurements. Is that exact or a measured number? You're absolutely right. Does that make sense? So 1, as you can see, counting gives you exact number. Okay? So when you go to the grocery store and you buy 3 dozen of eggs, exact. You go to the grocery store and you ask a clerk in the deli to give you about a pound of roast beef. The final amount of roast beef that you're going to get is measured number. It can be 1.07, 1.15, and it's measured to a certain significant figure because of the precision of the scales. We're good so far?
Yes.
Awesome. Another count of exact numbers, the definitions. For example, say that each 10 degrees of the Celsius scale, the temperature scale, remember? It's 18 degrees of Fahrenheit. Definition, people. That's it. That's defined. There's no significance. We can say it's approximately 18. Every 10 degrees are exactly 18 degrees in a different system. Does that make sense?
Yes.
You say, well, I don't want to use this. So 1 gallon is 4 quarts. Exact number. Various definitions of units. 1 mile is 1,609 meters. Exact number. We don't measure the mile, we know the definition of a mile in meters. Same way, like inch, 2.54 centimeters. Okay? Clear?
Yes.
Good, awesome. So those are your exact numbers. Another sort of a glimpse into the future test on this material. I give you a question, which of the following numbers is the exact number? Or which of the following examples is an example of exact number or measured number? Okay? Good? Now, this is very important, and this is one of the sort of harder concepts because you will have to memorize the rules on how to do the calculations with the significant figures. That makes sense. For instance, if you need to multiply or add numbers that have different number of significant figures. So we will need, I'm going to give you sort of a heads up. Addition and subtraction use the same rules. Division and multiplication use the same rules. Got it? So first, let's talk about rounding the significant figures. Why? If you divide 5 by 2. What's the answer?
2.5.
If you count significant figures, then the answer is 3. Because you have one significant figure in the number 5 and one significant figure in the number 2. So you can have only one significant figure in your answer. Does that make sense? So if you take a calculator and do 5 all over 2 division, calculator will give you 2.5. But you need to round it up to maintain the proper number of significant figures. Does that make sense? This is why we're going to focus on the rounding. So that's pretty straightforward. Let's say you want to round a number 1.347 and you want 47.9203. Okay, whatever. Now, say you want to round it to 3 significant figures, which is going to be 1.3 and then whatever the third figure is. Am I clear? How do you know which figure that is? That's the first number, first digit that you're dropping. If it's more than 5 or 5, you increase the last significant figure by 1. So what's going to be your rounding? 1.35. We clear? We good? There's going to be a question on the exam about rounding. Well, test. Well, quiz, whatever you want to call it.
When is the quiz?
Monday, next Monday. I told you I'm going to announce it a week before, so next Monday.
So we're only gonna do numbers? The significant?
No, it's going to be all multiple choice. There's going to be like picking numbers. I try to remove all calculations because I find it useless, honestly. You know, you can use your calculators. I don't want you to waste time on calculating. It's going to be a lot of, which number has 3, 4, 5 significant figures, the definition, stuff like that. Okay? Now, in sort of the same fashion, if you have a number 3.42179 and you want to round it to 3 significant figures,
3.
you look at this one, right?
Mm-hmm.
So this is 1, it's lower than 5.
Mm-hmm.
If it's 4 or 3 or 2 or 1 or 0, just drop this whole thing. Just drop. No increase. Does that make sense? Yes.
I have a question. How about that number is a 4? And then the next number is a 7,
3
9?
doesn't matter.
So
Doesn't
that's
matter.
just a drop.
Doesn't matter. You look only on the first one that you're dropping. That's it. Like, you see, let's say that's going to be 4, 7, 9.
Mhm.
I don't care. Still 3.42. That makes sense? You got it?
If that number's a 5, the 2 is going to go up to 3.
Yep. If that number is 5, it goes up to 3. Now, you cannot round it to 5 first and then round this one to 3. No, it doesn't work this way. You got to have the whole product of your calculations, and then you round it up to a certain significant figure. Am I clear? Cool. So this is some examples. Already figured. So this is the number that you're rounding. Can you see that? No. Well. Okay, that's pretty cool. Right, so you can see we rounded up to 3 significant figures. We drop 3, 4. Okay. Rounded up to 2 significant figures. We drop 2, 3, 4. 8.4. That make sense?
Mm-hmm.
And in the same fashion here. So you round this up to 3 significant figures. This number, The one that you're dropping is 8. So you have to increase the last significant figure by 1. So you're going to have 14.8. If you want to round it to 2 significant figures, the last number is that you're dropping, 7. Okay? You're dropping 7, so you need to increase 4 by 1 to 5. 1, 5, 15. Does that make sense?
Yes.
Be able to round it up. Okay? We good? Question. Any questions about rounding before we move on? I don't want anyone to get stranded in this. We got it?
Yes.
Cool. So, multiplication and division. We're going to do multiplication, division first, addition, subtraction second. That's your rule. You have 2 numbers, or 3, or 4, or 24 numbers that you multiply. You pick one with the fewest significant figures. Your answer should have the same number of significant figures. Okay? Let me show you. Here, first number, how many significant figures?
4,
Second number,
3, 2.
2. 0 is the placeholder. It's 2. Okay? What is the least? 2. If you do calculator, that's your result. Okay? Now you need to round it up to how many significant figures? 2. So you have to drop the last 2, 3, 1, right? You have to round it up to 2 significant figures. And when you round it up, it's going to be 8.6. Does that make sense?
So in the multiplication, the least significant numbers just gonna get the final answer.
So the lowest number of significant figures dictates you how many significant figures you're going to have in your final answer. So if you multiply a number with 7 significant figures by a number with 1 significant figure,
Then only one.
only 1. You may have 7, 27, 107. If you multiply it by a number with 1 significant figure, you have 1 in the answer. Is that clear? Are there any questions about it? Moving on. Bless you. So that's the example of 3 numbers. How many significant figures?
3.
3. 2, 1, 5. How many? Sorry. How many significant figures in the second one?
2.
2. How many in the third one?
3.
3. That's your calculator thing. And if you have a really badass big calculator, it may give you not whatever numbers, it may give you even more. Doesn't matter. How many significant figures you're supposed to have in the end?
2.
That's your answer. Does that make sense to you? Okay, we're good? Now with addition. Okay. What if a calculator contains less significant figures than you need? If you multiply 6 by 2 on the calculator, which I hope you won't, what's going to be the answer? 6 multiplied by 2. 12. Now, in this written expression, how many significant figures you have here?
2.
2. Oh, that's division. Okay, how many significant figures here?
3.
3. When you divide 6 by... If you multiply it, you're fine. Right? You multiply it, you're fine. Number 12 has 2 significant figures. You're good. Okay? When you divide it, the answer is 3. How many significant figures you have to have? 2. So what do? You put a decimal point
And then 0.
and you write 0. Does that make sense? Brilliant. Addition and subtraction. Now, this is easy to mix up, but when you do division and multiplication, you look at all significant figures. Is that clear? When you do addition and subtraction, you need to look at the decimal places. Okay? So your answer should have same number of decimal places, same number of digits after the decimal point as the number with the fewest decimal places. Let's take a look. This 3, how many decimal places in the first one? 3. In the second one? In the third one? 1. Which one has the least number of places? The third one. 1 decimal place. How many decimal places your answer should have? 1. So this is your sort of calculated number, but you have to round it up to 1 decimal place. Does that make sense? Do you see that? So this is your calculated number, 66.102. But it has 3 decimal places, and you have to have only 1. You round it up to 1 decimal place. Does that make sense? Here's your example. Another example. 2, 1. That's the calculated answer. You round it up to 1 decimal place. Are we clear? Now I'm going to ask a really hard question. Imagine that you have a problem, like, chemistry problem. You have to multiply, divide, add, and subtract. What do? You have like 3 divisions and 2 additions. Exactly. You multiply first and do all significant figures for all your multiplication or division parts. Does that make sense? And then, once you're done with your multiplication division parts, you add or subtract whatever you need to do. And then you start playing with decimal places. Got it? Okay. Any questions on the sig figs? Significant figures. So on the exam, you're going to have questions not so much calculating something, but more of, I give you a sum of 3 numbers. How many significant what's the answer? How many decimal places the answer is going to have? That makes sense? Or I give you multiplication or division. How many significant figures the answer is going to have? Good?
Yeah.
Of course, you're allowed, if you want to use a calculator, you're allowed to use a calculator. Okay? Deal? Prefixes, equalities, and eventually we will get into the conversion factors. So that's the metric system. You need to be familiar with the use of prefixes, and you need to be able to figure out equalities such as 1 kilogram is equivalent to 1,000 grams. Okay? That make sense?
Yeah.
So So in the international system of metric units, you can put a prefix in front of a unit to make it larger, make it smaller, and increase and decrease will always come as a factor of a number 10. You can increase it by 10, 100, 1,000, decrease it by 10, 100,000. Few things about prefixes, sort of a general rule. We have prefixes for 10 times more or less, 100 times more or less, 1,000 times more or less. Is that clear? After 1,000, we go from 1,000 to 1,000,000, from 1,000,000 to 1,000,000,000, from 1,000,000,000 to trillion, from trillion to quadrillion. So we're not going every degree of 10. Like, we don't have any prefixes for 10,000 or 100,000 more, okay? Or 10 million or 100 million. We jump through every 1,000 times, okay? Realistically, in your chemical calculations, in your patient analysis, you're going to use kilo, so up to 1,000. You're going to use down to micro, which is 10 in the power of negative 6, 1 millionth. Maybe nano, which is 10 in the power of negative 9, 1 billionth fraction. I can think of some human parameters that can be even lower, but that would be extremely rare. Okay? So far, good? So here's the example of prefix. For instance, unit of a mass is a gram, right? Gram of something can be a lot, especially if it's a drug. For instance, when you get your ibuprofen prescription, first of all, you can buy ibuprofen without the prescription, right? Over the counter, have you ever looked at the dose? It's 200 milligrams per pill, okay? So your prescription dose will be usually 600 or sometimes 800 milligrams. Now, if for some reason, I don't know if they have that drug form, but if you add extra 200, you can have 1,000 milligrams. 1,000 milligrams of ibuprofen will be equivalent to 1 gram of it. Does that make sense? So milligram is 1,000th part. You take 1,000 of those 1,000th parts, you make this whole thing again, the whole gram. That makes sense. Yeah. Micro goes millionth and so on and so forth. Here are examples of increase. So you need to know this 4. Okay? They don't follow any logic, really. No, seriously, like, there's no, like, I don't have mnemonic rule for this. Kilo is the 1,000, mega is million, okay, giga is billion, and tera is trillion. Okay? These units rarely used in chemistry or in medicine. Some of them are used in the military. You may have heard the expressions that characterize the power of the nuclear bomb. For instance, the bomb that was dropped on Hiroshima was called 10 kiloton bomb, which means the power of explosion was equivalent to 10,000 ton of conventional explosives. You know, if you hear about the explosion which has 10 megaton, means 10 million ton of conventional explosives. Does that make sense? It is also used in energy production. If you read about power plants, their power output will be characterized in the unit of power, which is watt. That will be like megawatt, gigawatt, how many millions or billions watt they can generate.
Computer data storage.
Oh yeah, excellent. Computer data storage, yes. We're now at what, terabytes? Yeah, terabytes, yeah. The picture of a black hole, they had something like several petabytes, which is the next level, which is 10 in the power of 15 bytes. Thank you for reminding. Appreciate that. Now, these units decrease. Deci is 1/10. Decimeter, okay? 1/10 of a meter. Santi is 1/100th. Does that sound familiar? Or sounds the same as the word cent? The English word cent comes from the same root, they cognate. Okay, 1/100th. Then you have milli, 1,000th. And then we start counting by thousands. So micro, 1/1,000,000th, nano is 1/1,000,000th, and pico is 1/1,000,000,000th part. Does it make sense? Those are the those are the prefixes that you need to know. Some of you may have noticed we never talked about the prefixes. Let me go back for a second. Hold on. I'm going the wrong way, I'm sorry. We never talked about 10x prefix or 100x prefix. 10x is deca, and 100x is hecto. So say 100 liters would be called hectoliters. 10 liters would be called a decaliter. Does this idea make sense?
Yeah.
Now, to my knowledge, the only industry where these units are used is brewing. They measure the beer output in decaliters. Huh?
It's most important.
Oh yeah. Oh, I agree totally. Yeah, but for some reason they use decaliters. Okay. So in medicine, quite unlikely. So far, prefixes, do they make sense? Now, what you can expect, which of the following units or which of the following prefixes corresponds to 1,000 times more? Kilo. Which of the following prefixes corresponds to 1,000,000 times less? Micro. Am I clear? We're good. Fantastic. So that shows you the relationship. So we have basic units, meters, liters, and then if we add the prefix kilo, we multiply it by 1,000. Okay? 1,000 grams is a kilogram. 1,000 meters is the kilometer. We're good? So if you would look at the units in some nutrition, that's a recommendation, FDA recommendation of protein consumption vitamin, calcium consumption, you know. So here you can see how much vitamin C you need to consume every day. 60 milligrams. So basically you take 1 gram, divide it in 1,000 parts, and you consume 60 of those 1,000 parts. That make sense? Now, let me ask you a few really simple questions. What is bigger, a gram or a milligram?
Gram.
What is smaller, a microgram or a milligram? A micro, because it's 1 millionth. What is, well, let's make it more complicated a little bit. What is bigger, a decimeter or a centimeter? Decimeter. Excellent. We will have to compare those units. Okay. Hey. Which one's bigger? Which pair shows you the correct relationships between the units? We're good?
Mm-hmm.
Cool. Now, for instance, what type of measurements are you going to be using when you work with patients? So how big is the meter? Approximately. Can you show it on yourself?
A meter, 100 centimeters.
Yeah, it's about right, yeah. Like, that's kind of about a meter from tip of my fingers to about here. Okay. So, which units would you use to measure the patient's height?
Centimeters
Centimeters.
or inches?
Centimeters.
Let's pretend that we live not in the imperial system, but in the metric system for a second. So centimeters. Can you use meters?
Yes.
Yes.
Yeah.
You're gonna have different number in the end. So say if somebody's height is 180 centimeters, in meters it's going to be 1.8. Okay? Can you use millimeters? I mean, you can. It's grossly inconvenient, you know. How much is kilogram?
1,000 grams.
Thank you very much. Like conventional measurement, the one that we used to. You go to the grocery store, what weighs about a kilo?
60 ounce. 60 ounce.
It's not 16?
16 ounce. Yeah.
No.
No, that's a pound.
It's a pound.
I tried to get away from imperial. Just let's announce it's as imperial free as possible, this space. So what product can weigh a kilogram? A what? Come on.
A pack of hot dogs? I don't know.
A pack?
Of hot dogs.
Hot dog.
Or like a pack of
Yeah,
lunch
it's
meat.
probably,
Probably 4 apples.
4 apples probably a little small. Quart of milk, the easiest. It's almost a kilo. Okay, something close to a liter, about a quart. That's a kilogram. Okay, 2.2 pounds. That's perfect. Okay, so basically, when you go and buy the standard like ground turkey, 2.25, that's about a kilogram of ground turkey. Does that make sense? Okay. Now, you're going to use, in medical practice, you're going to use not only meters or centimeters, you may use millimeters, okay? The diameter of, say, here's the nerve, I can tell the diameter of an artery will be measured in millimeters, okay? A lot of smaller measurements, like diameters of the retina will be in centimeters, but when you get to the special place in the retina called fovea centralis, it's a tiny little dot in the back of your eye where all the important information is focused on. So like you're looking at me now, or you're looking at the slide now, this image or this image is focused in that one tiny little dot, which is about 1 millimeter. Okay, so 100 micrometer in diameter, really small dot. That's the units that you're going to be using in your practice. That makes sense? So let's talk about some measurements. How do you measure? This stick gives you a measurement of 1 meter. That's your basic unit. Now, if you would look at the stick really closely, you will see a number 100 here. So 1 meter will contain 100 of centimeters, or 10 of decimeters, or 1,000 of millimeters. Very good. Good. Does that make sense? It's going to be all the same. So I can say that my height is 178 centimeters, or 17.8 decimeters, or 1.78 meters. That makes sense? Now, volume. We use liters in the health sciences. Now, it's kind of a weird, even in the metric system, there are some variations. If you would ask a physicist or an engineer, they will always use the volume of a cubic meter, which is enormously large, to be honest. Okay? Cubic meter contains 1,000 liters. That's a lot. Okay? The volume of human blood, I told you, for an average doll, it's about 5.25 liters. Okay? So that's a lot of humans you need to bleed to fill up 1 cubic meter. So we use liter mostly. So here you see an example. Deciliters used quite infrequently. And centiliters used infrequently. We mostly use, to be honest, liter and a milliliter. Does that make sense? Mm-hmm. Now, a couple more relationships. Whether we talk about the volume or the length. You take a basic unit, such as liter, and divide it into 1,000 parts. Each part, how would you call it? You take a liter and divide it into 1,000 parts. Each fragment, each part will be milliliter, 1 milliliter. Then you take another liter and divide it in 10 parts. And each part will be called deciliter. How many milliliters are in 1 deciliter? 100. Does that make sense?
Yes.
Okay, so you will have to be able to do the conversions like this. You will have to be able to go from not only from milliliters to liters, milligrams to grams, millimeters to meters. But I'm asking you, how many centimeters are in 1 decimeter? How many? 10. Because centimeter is 1/100th, decimeter is 1/10th. So I have 10/100th parts in 1/10th part. Does that make sense?
Yes.
Now, we, in medical field, we often use a unit called cubic centimeter. Cubic centimeter has the same volume as 1 mil. Okay? So when you see in the prescription to give a patient 5 cc of a drug, it really means 5 milliliters. And cubic centimeter, shown in this image, is the cube with the size of 1 centimeter. How big is the centimeter? Well, you can kind of have an idea. The nail without overhanging part, okay? Without the edge, the nail is about centimeter, okay? So that's the length of the nail is centimeter. Imagine a cube that size. We good so far? Now here comes sort of a tricky part, which let's figure out how many cubic centimeters are in 1 cubic decimeter. Okay, so do you understand? Let's start with the we're talking about. So that's the cube. Well, as good as it can be. Okay, can you see the cube that I drew? So imagine that the size of this cube, size of the side, is 1 centimeter. What's the volume?
It's 1 milliliter.
1 cubic centimeter. Right? 1 milliliter, you're absolutely right. But it's 1 centimeter cubed. You with me? Now, size of that cube, as we just mentioned, is 1 centimeter. How many centimeters in 1 decimeter?
10.
10. Imagine we draw another cube, which is shown here. So this cube has a size of 1 decimeter, right? Now, how many cubic centimeters are going to be in this cube? So you need to multiply 10 centimeters on one side by
Another
10 centimeters on another side. So you have to multiply width, length, and height. 10 by 10 by 10 gives you 1,000. So you're going to have 1,000 cubic centimeters in 1 cubic decimeter. Okay? Do you see that relationship? 1 cubic decimeter is equivalent to 1,000. I'm sorry for the drawing. This pen is terrible. 1,000 cubic centimeters. You with me? Now, the definition of a liter is that liter and a cubic decimeter are the same. Does that make sense? By definition, 1 liter is the same as 1 cubic decimeter. Am I clear? Now, are you ready for some calculation challenge? Really simple, really. So imagine you have a cubic meter, a cube with a side of 1 meter long. You with me?
Yes.
How many decimeters you have in 1 meter? How many decimeters? Huh? How many? Hold on, no. Hold on. How many? Say again?
10.
10. You have 10 decimeters in 1 meter. You follow me? So, how many cubic decimeters you're going to have in 1 cubic meter? 10 multiply by 10, 1,000. Bingo. 1,000. So you have 1,000 cubic decimeters in 1 cubic meter. Now look at this. Cubic decimeter is equivalent to what? 1 liter. So in 1 cubic meter, you're going to have 1,000 liters. Does that make sense? This is useful to know, when you think about, like, even conventional measurements. I don't know, how much water you spend every day. Does that make sense? Is that understood? Do you understand the conversions? We're going to play a lot with the conversions, so you feel comfortable with that by the time we get to, like, the actual charge. Question? Question? All good? Awesome. Okay. So far, before we move to mass, I want to highlight one really important thing. If you have a unit of length, like a meter, can you define a unit of volume? Yeah. You just say, okay, my unit of length is 1 meter, my basic unit of volume is 1 cubic meter.
Yes.
So you express volume through length. Does that make sense? That is really convenient. That's a huge convenience of metric system. Because you can really define a quart through inches. I mean, you probably can, but it will be something royally weird. Okay? Does that make sense? Now, what about mass? Same story, 1,000 grams, 1 kilogram. Centigrams used really infrequently. When centigram is 1/100th of a gram. More frequently we use milligrams, micrograms, stuff like this. Okay? So basically, for practical purposes, you're going to be using grams, kilograms, milligrams, micrograms in your practical applications everywhere, really. Are we clear about this? Okay. Now, if you're curious how we define mass, they replaced it recently with something, but there used to be a standard of a kilogram, which was basically a cube of, I think it was platinum cube, which was stored in a very precise conditions in Paris. That's it. It was just the actual kilogram. That was like the defining thing. So every country compared their standards to that French standard. Okay? Same way in Paris there was a unit for a meter, which was like a physical ruler, which was stored in the super constant conditions. Eventually it was replaced by some really awkward definition, which is the certain number of wavelengths of a certain spectrum line of a certain chemical at certain temperature. Like, you read it and by the middle, screw that. They should have left the ruler. Okay. But yeah, we do have standards. And what's important for our understanding of the relationships between these three main measurements, the length, the volume, and the mass, is first that we can express volume through length. Does that make sense?
Yes.
We can. But next question is, can we express the mass? Can we derive metric unit of mass through, I don't know, volume maybe? Turns out, yeah, we can. If you take 1 cubic centimeter of water, 1 milliliter of water, at the temperature of 4 degrees Celsius, it's going to weigh 1 gram. Does that make sense?
So in different temperature, the water weight different?
Yes. Different temperatures, water has different density, so it's going to weigh different. Okay? I mean, the certain volume is going to have different mass. That's, so the higher the temperature, the lighter, quote unquote, the water. Does that make sense to you? Yes.
You said 4 degrees Celsius.
4 degrees. As far as ever, it's 4. You get 0.999 at 4 degrees Celsius. Practically 1. Okay. That makes sense? So you can, using water, you can express mass through volume in some sense. We good? That makes sense. Now, let's talk about conversion factors. What do you need conversion factors for? In metric system, the conversion factors would be extremely simple. Look at this, the first line. 1 meter is equivalent to 1,000 millimeters. Are you with me? So you can write it down this way. Now, again, I will keep apologizing for that pen. Thousand millimeters in 1 meter. That's the conversion factor. Does that make sense?
Yes.
1,000 millimeters in 1 meter. And you can realize that in metric system, all your conversion factors will be different exponents of 10. It's going to be 10, 100, 1,000, maybe on top, maybe in numerator, maybe in denominator, but it's going to be all, 10, 100, or 1,000. Does that make sense?
Yeah.
And this is the great advantage of the metric system. In imperial system, conversion factors, will be not as conventional and convenient. So for instance, 16 ounce is equivalent to 1 pound. So you can write a conversion factor from pounds to ounces as 16 ounces per 1 pound. Does that make sense?
Mm-hmm.
The example that you provided, pounds to kilos, 2.2 pounds in 1 kilo. Does that make sense? So those are conversion factors. So you do it all the time when you talk about time, no pun intended. So you say that 60 minutes are in 1 hour. Or you can say that there is 1 hour in every 60 minutes. That makes sense. You can say same for the metric measurement. That 100 centimeters are in 1 meter and vice versa. Okay? Does that make sense? Now, a really important note. Conversion factors and how they play with the significant figures. Inside of each system, equality is exact number. How many ounces are in the pound? 16. Can it be 16.1? Almost? No, it's a definition. 16 ounce. That makes sense? How many meters in a kilometer? Meters in a kilometer. 1,000. 1,000. Perfect. So 1,000. Can it be 999.9?
No.
No, it's a definition. Inside of the systems, the conversion is exact number. Does that make sense? Between systems, there is one number obtained by measurement. Okay? So between metric and US, there are significant figures. you can take a pound and put it on the metric scales. And that'll give you, depending on how precise scales are, it will give you a certain number of significant figures for the number of grams in 1 pound. That makes sense? Now, the only exact number that establishes the relationships between the imperial and the regular system, the metric, is the number of centimeters in 1 inch. That is defined. Does that make sense? So definition, 1 inch is 2.54 centimeters.
So does that mean 1 pound is not exactly 2.2?
No, you can measure it more precisely.
Okay.
Like for instance, we do converse, like when my wife cooks, she often measures in metric, okay? Quite often, really, when she takes, like recipes from Russian websites. And she has to convert pounds into grams, and vice versa. So she uses usually 1 pound is 450 grams, which is not precise. I think like if you measure it more exact, it would be something like 4.4 and some decimal, blah, 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 blah. 450 is fine. So she basically works with 3 significant figures. For cooking, that's enough. Does that make sense? So the only one is inch. So it's strictly 2.54. There are no other numbers after 4. That's a definition. Does that make sense? Well, obviously, all fractions of an inch and all multiple inches can be derived from that. So if you think about it, inch is 2.54. How many inches are in the foot? Well, you multiply 2.54 by 12, you get exact measurement, exact number of centimeters in a foot. But if you take a tape with 1 foot on it and you will measure it, it's going to be a measured number. That makes sense? So here's some conversion factors. Now, I do not remember if there are questions about the conversion. As far as I remember, on the quiz, obviously. I'm talking about the quiz. I tried to limit it to pretty straightforward imperial conversions, and I try to get away from imperial as much as I can, really. Okay, because you can Google it. Like these tables, nobody needs them. Just go into Google on your phone, say how many inches are in 3 meters. And you have a freaking calculator. Like you just put 3 meters. Okay? So nobody needs these tables. I do ask about the metric conversions. So basically, it all boils down to meters, certain number of meters to kilometers, certain number of millimeters to meters. Do I make sense? That you must know. That's all based on tens, so you should be good. I do not ask some freakish stuff. How many centimeters in a certain number of yards, who cares, right?
Shall we remember all that?
Oh, screw that. No, I don't. Like, let's be honest. For real life, what do you need to remember? You need to remember inch, which is 2.54. The easy way, I'm going to teach you some easy ways. The easy way for ballpark estimation, now that's not for the exam, that's for your life. Ballpark estimation, 1 inch, 2.5 centimeters. Okay? How you can go from inches to centimeters? You take all the inches that you have. Say somebody is 60 inch tall. You following me? Multiply it by 10, divide by 4. 60 multiplied by 10 is 600, divided by 450, about 150 centimeters. Is there going to be some error? Sure. It gives you a ballpark. Okay? Now, pounds. Pounds to kilos, it's kind of an elaborate way. Take pounds divided by 2. Say 300 pounds. Okay, you divide it by 2 gives you 150. Then you take that 150 number, take 1/10 of it and subtract. So what's 1/10 of 150? 15. You take it out, 150 minus 15 gives you 135. It's about 135 kilos. Is there going to be some error? Sure. Okay. And it's all like ballpark-ish. Okay? That makes sense? Kind of helps. I had some issues myself. You know, what kind of confuses me, and still I don't really know whether the certain website asks for inches or feet in inches. So, like, you know, it asks, what's your height? I'm 70 inches. No, not 69. Okay? So I put 69, and it turns out it asks for feet in inches, so I'm suddenly 6 feet 9 inches tall. Okay. This is how you write metric conversion factors. This is how you write metric US, metric imperial. Okay. So say 2.2 pounds in 1 kilo. You can also do 450 grams in 1 pound. Totally legal. Well, 454, you know what I'm talking about. That makes sense? Kind of a general idea. So, why do we need conversion factors? Sometimes it helps us to understand what's going on in the problem. So like here, the car, its speed is 85 kilometers an hour. What does it tell you? That the car goes 85 kilometers, it travels 85 kilometers in the time of 1 hour. Or that it takes 1 hour for a car to travel 85 kilometers. Okay, now that's, you have to really, it is really visual. You have to understand, not just take this numbers at sort of a face value, but understand what's behind them. Does that make sense? Now let me ask you this. You drive the car down I-90. Okay, I-90 eastbound, somewhere beyond Madison, towards Pennsylvania. Okay? And your speedometer breaks down. You have a passenger in the front seat, and say your GPS, like all GPS in the world, went down. So you cannot pull up the GPS on your navigation system, you cannot pull up GPS on your phone. All you have is the good old time device, like watch, and your eyes. Can you still know your speed? Sure. How?
Mile markers.
Sure, yeah. You count how much time, it's your conversion factor, how much time it takes for your car to go 1 mile. Does that make sense?
Yeah.
And say you measure that you go 1 mile in 1 minute. Well, you say, okay, that makes 1 mile
60 miles.
exactly per 1 minute. Say, how many minutes are in an hour? 60. So how many miles do I make in an hour? 60 miles. Does that make sense? That's your conversion factors. Now, that's important. dosage problems. Forget about cephalexin. You're not going to be measuring your own cephalexin in any foreseeable future. You may figure it out for a patient who has, let's say, urinary tract infection, which cephalexin is intended for. So, I believe third generation cephalosporin antibiotic, which treats UTI, really good drug. So say, let me put it in the real clinical case. So you have a patient that comes in the emergency room with a UTI, right? So the lab ran all the tests, blood in the urine, white blood cells in the urine, flanking pain, painful burning urination, all typical signs and symptoms. So what you do first? First, you pump the patient with IV cephalexin. Whatever, you pumped, okay? The IV bag emptied, you send the patient home. And the prescription states that the patient should take 500 milligrams of cephalexin a day for 10 days. One capsule is 250. The prescription says 500 mg a day. How many capsules a day?
2.
2. How many days?
10 days.
How many capsules?
20.
That makes sense?
Yeah.
That's or the doctor says, give this patient 1,000 milligrams of cephalexin. What you do is say, all right, 1,000 mgs. How many capsules?
4.
One capsule per 250 milligrams. 250 and 1,000 gives you 4 capsules. Does that make sense?
Yeah.
Got it? The conversion factor idea. It's really important for the drugs. Okay. Now, let me do some technical magic.